In principle, a rigid object could experience both linear and rotational accelerations. Thus, for a rigid object to be in equilibrium, both its linear acceleration and its angular acceleration must be equal to zero. We know from our earlier study of linear dynamics, this means the net external force acting on the object must be equal to zero in accordance with Newton's second law. For two-dimensional linear motion, this means the sum of the forces in both the x and y direction has to be equal to zero. We must also consider the rotational motion of the rigid object, which cannot change under equilibrium conditions. Since it is torque that produces changes in rotational motion, the sum of the external torques acting on a rigid object in equilibrium must also be equal to zero. Let's now summarize the definition for rigid body equilibrium. A rigid body is in equilibrium if it has zero translational acceleration and zero angular acceleration. In equilibrium, the sum of the externally applied forces is zero, and the sum of the externally applied torques is zero. Let's now look at the reasoning strategy for analyzing the forces and torques acting on a rigid body in equilibrium. The first four steps of the strategy are essentially the same as those outlined in section 4.11, where only translational equilibrium was considered. Steps 5 and 6 are now added to take into account any external torques that may be present. Step 1. Select the object to which the equations for equilibrium are to be applied. Step 2. Draw a free body diagram that shows all the external forces acting on the object. Step 3. Choose a convenient set of coordinate axes and resolve all the forces in the free body diagram into their x and y components. Step 4. Apply the equations that specify the balance of forces at equilibrium, namely the sum of the forces in both the x and y directions is equal to zero. Step 5. Select a convenient axis of rotation. The choice is arbitrary. Identify the point where each external force acts on the object and calculate the torque produced by each force about the chosen axis of rotation. Set the sum of the torques equal to zero. Finally, step 6. Solve the equations obtained in steps 4 and 5 for the desired unknown quantities. As a problem-solving note, the sign of the torques that go into the sum in step 5 will be determined by whether the force producing the torque tends to rotate the object clockwise or counterclockwise. For example, here is a diver standing at the edge of a diving board and the corresponding free body diagram. The axis of rotation was chosen where a bolt holds the other end of the diving board fixed. Of the forces in the free body diagram, only the diver's weight, W, and the normal force from the fulcrum, F2, will produce a torque about the axis of rotation. Since F2 wants to rotate the board counterclockwise, its torque will be positive. And since W wants to rotate the board clockwise, it will produce a negative torque. Therefore, in step 5 of our reasoning strategy, the sum of the external torques will be given by the following: the torque due to F2 minus the torque due to her weight.